All right, welcome back to the Kitchen Research Group. Today I'm going to give a brief video overview of a recent paper that we have published in this collaborative project between my group, Stefan Bernhard's group, and Joe Millstone's group. The students that did this work were Zoe, Eric, Maya, Paige, and Sarah. And what we've been looking at are the activity and stability of nanoparticles that we form in situ for an application in photocatalytic hydrogen evolution. So this work was recently accepted in ChemCat Chem and was funded by the Department of Energy in this award listed here. All right, so the thing that we're looking at in brief is that we have a in situ one pot experiment where we have metal salts and we irradiate them and we make colloidal nanoparticles that evolve hydrogen in the irradiation. And what we found is that if you don't stabilize the particles, not surprisingly, in retrospect, they precipitate out of solution, leading to a loss of activity. And this is known in the nanoparticle community, but most people pre-synthesize particles with these stabilizing ligands. And we have this one-pot in situ synthesis. And what we found in this work is that we can add stabilizing ligands like PEGSH, and I'll show you some other examples, and it leads to stable colloids with longer-term activity. And we show that by comparing it to in situ synthesized particles with and without these ligands to pre-synthesized particles that are stable. We also found not every ligand works, so you have to put some effort into finding the right ligand and the right ratios of those, and I'll show that just a little bit as we go. All right, so what is our one-pot synthesis? We have this photoreactor that the Bernhard group has developed. It has 96 wells that are shown down here. We fill each well with metal salts, with the solvents, with the photosensitizer, and then we shine light on it here. And there's a hydrogen-sensitive tape that changes color that allows us to quantify the hydrogen. And roughly the mechanism is photons come in, we have this photosensitizer cycle that goes through an excited state. There's a thing that gets oxidized here. Typically it's TEOA, but it can be other molecules as well. And then some of the reducing power of that goes into either reducing metal salts to make the nanoparticle that's depicted here, or reducing protons to make hydrogen. So that's the basic idea that we have, and we've been looking at lots of different metals and different fuels, different photosensitizers, etc. All right, so if we just put in metals like gold and copper, here we have gold on the left, this is a mixture of gold and copper and another mixture of gold and copper, and we go through several cycles. What happens is we get these very big nanoparticles that literally get so big they fall out, they crash out of solution, and we see very low activity, right? So this is the hydrogen production over time. After the third cycle, the first cycle looked more interesting and it showed some activity, but after a few cycles we see this lack of stability. Now if we do pre-synthesized particles, so the Millstone group is very skilled at making these. They can make gold particles, the gold copper particles, and these are pre-synthesized so they have ligands that stabilize them and prevent them from aggregating. And then this is what the activity looks like after the third cycle, and it still shows quite good activity, and you see no change, no substantial change, maybe a little bit of growth. That's to be expected. But otherwise, these are very stable compared to the in situ case. And the primary difference here is the presence of the stabilizing ligands, like PEGSH. So if we add that to our synthesis, just make that an additional ingredient in each well, then what we find is after 3 cycles we also have stability, and instead of seeing those big aggregated particles, we see these stable nanoparticles. And so we're able to stabilize the nanoparticles by adding the stabilizing ligand to the in situ synthesis. Now, not all ligands will work. So BSPP is a ligand that is known to stabilize gold, but it does not stabilize copper. And so when we use, instead of PEGThiol, a different ligand like BSPP, then we can see stabilization for gold particles, but not stabilization for those that are containing copper. Because BSPP doesn't stabilize copper, it doesn't interact with this surface atom strong enough to provide that stabilization. We looked at a few other metals. So PEGThiol also stabilizes metals like nickel and cobalt and palladium. So those are shown here, nickel, cobalt, and palladium. If we don't use any ligand, you see these look totally dead and very uninteresting. But if you have the PEGThiol around, after 3 cycles, you see all of them are fairly active. And so this is an important point in thinking about how we do use this high throughput tool for screening. When we don't see hydrogen, we should ask ourselves, why don't we see hydrogen? Is it because we didn't make an active material, or is it because the material is inactive? And what this suggests is that when you have no ligand, that you do make nanoparticles. The cobalt looks somewhat amorphous, but these things all crash out to the bottom, and so it's not that they're not active, because they're very active when we have little stable nanoparticles. So clearly it matters what you make in this kind of screening experiment. All right, so that brings me to the conclusion of this video brief. What I showed you is we can stabilize in situ synthesized nanoparticles with the correct choice of ligands, and this leads to longer term activity. And some ligands only work for some metals, but PEGThiol is a good choice. It works for gold, copper, palladium, nickel. This should probably be cobalt, but spoiler alert, it also works for iron. And I'll talk about some follow-up work that we've been doing in another paper that was recently accepted in the next couple of days. So I hope this was interesting, and if you want to see it, this is the DOI for the paper. It will be in the video description, so you can just click on it from there. And thank you for paying attention to this video brief.